In this video, we're going to look at Houdini's new Whitewater SOP solver tools to create bubbles for our simulation. Let's go and set up our Whitewater simulation. So I'm going to come up to the top level here, and I'm going to make a new geometry container. Let's call this, let's call this bubbles. Because I'm going to create bubbles. I'm going to use the Whitewater tools to create some bubbles to help with the interaction down here and up at the top there. So bubbles are made basically where the water, at least at the small scale, goes in and splashes around and traps little bits of air that create the bubbles, and then they come up to the surface and float around a bit before popping. So that's the kind of thing I want to do. I want to sort of look for where the areas of high pressure are, and also where it's swirling up a lot, because that's generally where the little air pockets are going to get made. And hopefully generate some particles that I will use for rendering what looks like bubbles. So in Houdini 20, we now have some excellent, let's call this actually Bubbles Sim. We have some, let's turn this off as well. We have some excellent new tools for doing this. So the first thing I want to do is just use an object merge to bring in my cache data. So I'm just going to click on the little browser here. Let's open up the water simulation. Then we should have combined cache. There we go. Set this into this object. And look, there's our combined cache data. So let's just pop a null in, because this is what we're going to use to source the Whitewater from. So we'll call this cache. I like to color those red. So we're playing our cache through, which is all good. And depending on how heavy it is on disk, depends on how quick this is going to load in for you. So previously, we'd used the shelf tool to create Whitewater in the fluid tools here. There it is, Whitewater. And this is create a full-on dot network with everything else. And since we've been using the SOP flip tools, which have been around in a couple of versions of Houdini now, the Whitewater tools have joined their ranks in becoming SOP-based tools as well. You still got the option of using Whitewater in DOPS, but they've simplified stuff and bubbled it up to the SOP network here. If you hit tab and type Whitewater or white, you'll see we've got a bunch of nodes here. So the main one we're interested in is the source, because the source is going to create the emit field and generate it around the behavior of our fluid. And then we feed that into the solver, which then calculates how the Whitewater should move around. And then we've got this post-process, which allows us, after we've solved it and cached it, to do some final processing to turn it into either volumes for foam or spheres or whatever else we want to do. So, excuse me. So the first node I want to do actually is the Whitewater source. Now, fortunately, these tools are pretty similar to the dot-based tools. So if you're familiar with them, I'm not going to go through all the basics, because there's a few videos out there in much more depth and detail on Whitewater. But I will go through the basics of it, but it's pretty much identical to what you'd already be used to having used the dot tools, which is pretty handy. So you'll notice we've got the usual different inputs. If I hold my cursor over the first input, you'll see this is our liquid simulation. So that's what we plug the cache directly into. This second one is the container. This has the information about the container, as in the voxel size and stuff like that. This third one is the collision input. So if we've got anything to collide with, which we do, we'll add that in a moment. And then we've got extra sources. So here you can plug in other particle sources or point sources to generate your Whitewater from, or another emit field, that kind of thing. So you could merge multiples together and use that as a source to generate these, add the sources together rather. So here we've got the extra sources here. So you just add a particle with an emit attribute and it joins in here and adds that to the source that you want. We're not going to look at that really. What I am going to do is just plug this cache into the second input here, so we update the container information there. So this will give us the sort of right resolution and things like that. So it's picking up sort of these detail attributes for us. This is why we also made sure that we had our pressure field here and our vorticity as well. And particularly ID, we'll use ID a bit later on as well. So these are the fields that I wanted to carry through: the pressure, the vorticity, and the ID. These will be useful for generating from the white water here. So the first thing we can notice is we've got these various masks. So the mask just basically tells it where it's not going to emit particles from for us, or source them from for us. So the speed range here, it's going from a speed to a 2, from a 2 to a 4. And we're not sure what speed we've got. Let me step pause a few frames and see if we get a result. Now my fluid is relatively smallish scale, so the speed is not going to be that fast compared to a large scale water sim, which is what this is mostly designed for. So we might have to do some adjusting here to get a result out of it. So if we have a look, we're not really seeing very much, which is interesting. So there's a couple of things we can do for that. We could just pop a null on this output to see if there's anything there. We can see we've got the volumes, but they're quite small. I mean, we're not seeing very much at the minute. The other thing we could do is we can pop a null on this other output here. This will allow us to visualize points. This takes sometimes a bit of a second to display. So here we'll output points. We go to visualizations. This will output points to see what we're doing. Now, this whitewater scale generally needs to match the, I found that it needs to match the resolution of our sim. We set this to 0.002. And as soon as I bring that down, we start to see some particles or some sourcing appearing from our simulation. Now, this isn't a simulation, this node. This will just process whichever node you're on. So you can jump forwards to a different point in the sim, say over here, and it won't try and process all those frames up. It's not a simulation. So we can just jump to sporadic frames and test it out. And you'll notice these points have got colors on them. These colors relate to here, the curvature, acceleration, and vorticity. So we're actually creating the green points from the acceleration, the blue points from the vorticity, and the red points from the curvature in the surface. And that we can also use pressure, deformation, and some other things which aren't turned on at the minute. So let's go back to our emission for the moment. In fact, if we go to sources here, we'll see we've got emit from curvature, emit from acceleration. As I turn them off, you'll see they disappear, and there's the emit from vorticity. So they all turn off for the minute. And what I'd like to do is turn on the pressure, because I want to generate these guys from the pressure. We can also scale the pressure here with this value. If we put in a lower value, you'll see we get less points. And if we put back to 1, we'll get more points there, which is pretty handy. We can also emit this from the vorticity, which is what I wanted to do as well, which is how much it stirs it up. The vorticity is like the rate of change of the direction of velocity. So it's how much it stirs up the fluid. And you'll see this is this dark blue one. You can click on compute range, and what this will do, it'll pick out the range of the vorticities for you. So we've got a much larger range here. That's pretty much a 0. And it's up to 1,000 here. And you'll see we get a different value there. So if we revert this back to the defaults, you'll see we're a more dense distribution. Interestingly, if you go to different frames, see this is peaking at 992. Obviously, you're going to get different results, because what this does, it just reads the calculates these values from that spontaneous frame. So if we just run forward a little bit, let that calculate. Again, we can compute from the range. You'll see it's roughly about the same. That'll do. So we could leave the vorticity like that once we've set the range. Let's go back to a different frame, see how that looks. And I'm not really going to use the acceleration or the curvature because I don't think it's moving that quick to create bubbles at this small scale, or the curvature, but definitely how much it's stirring it up, and also the pressure here, particularly where it's impacting at the bottom, we want to generate our particles from. Let me look at the defaults here again. I might leave the defaults there because I just want a bit more density going on rather than remapping it to the range. We can get finer control here. I just want to create a lot of these particles. So we can also remap our vorticity actually. Let me just show that. Let me turn the pressure off for a minute. We can turn on remap. Now the remap's not going to really look like it's having much of an effect unless you do compute the range here. So let me compute the range. And there we go, we see it looks a bit thinner. So basically this is the low end of the vorticity and this is the high end of the vorticity. So we'll see we're getting more particles where it's much more swirly and a lot less where it's less swirly. So if I bring this up, we'll clip off the less swirly ones. So we'll only see vorticity for the particles being emitted for where it's really, really high vorticity, which is just down in this region here. So if you want to use the remaps, you must get the range in a lot more accurately, otherwise you won't see much of an effect on the remap there. So again, if you obviously put this up like this, it's just going to pretty much emit it through the whole range quite uniformly. So you could play with the remapping if you want. Give it slight exponential curve, something like that maybe. Or you might not want to use the remapping, you might just want to revert back to defaults and just leave quite a dense amount in the swirly nature there. So it depends what you want to do. I might actually leave that on a little bit, something like this. Let's put pressure on too. There we go. And we can do the same for things for acceleration and curvature, but I'm not going to use those in this example. So the other thing we can do is go to the masks here and just drop the speed range down. So this is going to clip it depending on the speed. So here I'm going to allow slower speed particles to calculate their vorticity and their pressure. So if I bring that down, we should get a bunch more particles going on here. So there we go. So I'm allowing slower particles now to calculate their vorticity and their pressure. And we'll see there's a lot more pressure in these smaller speed ones. This is why we call this a mask. I might actually bring this down a little bit further because I want to see sort of being able to source stuff that's just under the surface over here. Small scale liquids, you might want to reduce these numbers down so you see particular effects that you're after. So I'm allowing slower speeds to generate my bubbles because this is going to be like a bubbles pass. So that's kind of interesting. Again, we won't know how much of this will look until we actually cache it up and send it through the solver. So what I'm going to do is I'm going to leave this for a minute at this stage. Let's go back to frame 1 and let's save and let's set up the solver bit. So yeah, it's the reason that slows the visualization. If I turn off the visualization and then jump forwards a frame, you'll see it's a lot quicker. There we go. It's a lot faster. So just displaying the points is a lot slower for you. There is a way that we could visualize this. So we're not really seeing very much. It is actually a volume there called the emit volume, and that's what we can actually preview as well. And we could do that with was it a primitive properties node, if you remember? So we could plug this in. And here we can choose to look at the emit volume. So let's go to volumes, turn on the visualization. And let's increase this density quite a bit. There we go. So if we increase the density, we can see there's the emit volume. So this is where it's going to emit the bubbles or our white water from, which is kind of nice. We could maybe make this a bit more dense to visualize that. Cool. So this might be a quicker way to visualize what's going on, although you don't get the color display stuff going on there. But with the points, as you saw, that's quite slow to process if you're visualizing those. So let's add the solver into the mix. So if we do Whitewater solver, we can plug, well, let's just plug this straight in. Plug these 3 inputs straight in. Oh, the one thing we do need actually is the collision. Let's bring the collision in. I'm just going to copy this object merge and call this this null collision. And let's go and find our fountain object. So let's open up fountain out. You know, we're bringing that in. Got this geometry here. Now, for this to work, we actually need to convert this into a VDB. So what I'm going to do is going to do VDB from polygons. And we'll see that looks pretty coarse. What I like to do is to make sure I get the right resolution of this is just do a VDB convert and convert this back to, where is it, VDB convert this back to a polygon. Ooh, put that in the first input. Let's set this to polygon, and then we can see the kind of resolution we're dealing with, and that's a bit too coarse. So let's reduce this to 0.005, let's say, and that's probably quite good enough. We should check what resolution we did the original with, but I think 0.005 is going to be more than good enough for us. So what I want to do is not plug in this mesh, plug in the VDB from polygons here into this collisions tab. So what that'll do is just make sure we're not sourcing anything that's inside the collision surface itself. It's going to subtract stuff for us. So if I just disconnect that, see it helps change the way it looks. Adds the collision in. If I turn this off, see it doesn't really have much of an effect. So really the collision does want to be a VDB there, I believe. So yeah, the reason is you would pass this output. Actually, if we go to the water sim, where's the water sim? All the way up here. You'll see we have the collisions output here. So this collisions output outputs a VDB. So let me just go back to frame 1 because that might be a bit slow. Let's just pop a null in there. And you'll see that collisions tab, is that actually coming out as a collision there? Yeah, it's the surface field here that's going to become the collision. You'll see these are VDBs. So let's just get rid of that. So that's why here you want to be plugging in this VDB. What you could do actually, instead of creating the VDB here, is we could go back to the water sim, and then we could just pop out a null, and then there's our collider here. So if you look here, this is the one that's creating that surface. So we'll call this collider VDB. So if I just copy that null, then we could get what we can do is on this object merge, just place that in here. So now I'm bringing that VDB, and we could just bypass. We don't need to make our volume self. So if we just look at the convert here, see it's the same. Basically, is that 594? So yeah, it's roughly the same, basically. But yeah, you could do it either way. It's up to you. So yeah, we've plugged that in there, and then that collision's coming through down into the solver. That's the important bit. So on the solver here, we can notice actually that the collision doesn't look right. That's actually correct. When I look at this guy here, when I'm bringing in this VDB, if you remember, I've cropped this, haven't I? I've used this bounds, and we're only getting it within that region, to be fair. So this Philip collide's only getting that bounds there. So it's probably not the best one to use. So what I can do really is just use my VDB version here. Let's just plug that in instead. And there we go, we get the full collision surface going on there. That look the same? Let's just switch that out quickly again. Yeah, it's pretty much the same, it's just cropping it, which is fine. And I think that's a slightly higher resolution, so let's maybe just drop this down to 0.002, which I think is similar. That's what we had set in our particle separation. Actually, that was 1.5, so this should be 0.003 really, if it's the same size fields. We just abort that. So yeah, we've got the fields here. There's 0.003. Let's put that to a 3 instead. And it should be a similar resolution to what we would need. So just wait for that to process. There we go. Let's go back to frame 1. Our simulation's trying to run through from 2 different frames there. Good. So what do we need to change on our whitewater source here? So that's the other thing. If you here we change this whitewater scale. If you put your cursor over it, so this needs to be the same as the whitewater scale in the solver. So if we go to the solver, this is our whitewater scale here. So let's put that to 0.002 as well, which matches the kind of resolution that we're dealing with. Now, what I'm going to do is I'm actually going to leave the settings at default for the minute, because what I want to do is, first of all, if we select the whitewater source, you'll see that is quite slow to process. There we go. It's not the quickest of things. And I think I'm happy with this sourcing, and I can do a lot against the sourcing with the actual solver here as well, because this will generate how it moves afterwards. So what I want to do is create a cache, so I can cache out this source, and then I can cache out this independently. And that way, if I'm just tweaking the solver, it'll be a lot faster than trying to solve the source and the solver at the same time. So let's just pop in a file cache. Let's just pop this over here. Let's call this file cache whitewater source. And then we'll pop another one down here, and we'll call this whitewater sim. So one will catch the other one. Now this top one here, it doesn't actually need to be a simulation, so I'm going to turn off a simulation. And again, I'm going to build a top network so I can process this one in parallel, and then I can process this one afterwards. And we'll do that with the default settings to see what we've got, then we'll come back and tweak it afterwards. So for that, let's create a top network. And what I'm going to do is I'm just going to be cheeky and dive inside this source. I'm going to select the render node and do Control-C. That way I can easily go inside the top net and do fetch. So ROP fetch. And then in here I could just paste that path. Let's just choose relative. So that just is a quick and easy way of bringing that in. So that's going to be our source here. Now remember I said this doesn't need to be a simulation. So we do want to choose the frame range. And I've got 200 frames, so I'll do, if I do batches of 50, that means 4 processes will kick off simultaneously. So I think that should be fairly optimal for my machine. In the local scheduler here, I'm going to set this to all the CPUs except for one. So I'm going to batch up this job, so hopefully it'll go a little quicker than just doing all 200 sequentially. So we want to wait for all of those jobs to be finished, so it'll wait for all, like we've seen before. And then we want another ROP fetch to do the actual simulation. So here we do want to do all frames in one batch because it's a sim, so don't forget to switch that back. And then here, let's go find the other file node. And there you go, it's the one above. There we go, it says there wwsim, and there's the render node. So we've got the sim here, and we've got the source there. So this should be able to automate this process. We've turned off simulation there, which is good, and this one's got simulation turned on. Let's just make sure this says load from disk. So those work. Let's turn on the display of that one for the minute. And then all that I need to do now is save the scene and do Shift V, or you could just right click and do dirty and cook this node. You'll see that Shift V. So there we go. This one's waiting because of the wait for all, and there's my 4 batches of 50 frames, which is taking up 4 processors of my machine there. So if I just have a look at my performance, we'll see that's taken up quite a bit of RAM, 70 odd gig, but I've got plenty of RAM. So obviously, if you've got less RAM, all you need to do is maybe make larger batches. So if you do batches of 100, then you'll only have 2 processors going. And if you do it all in one batch, then you'll get 1 processor going. So that's what I would advise if you don't have as much RAM. But if you've got the RAM, you can start doing them in batches like this and take advantage of sort of this parallel processing across your CPUs there. So what I'll do is I'll just stop this video, and then we'll come back once that's cached. So if we come back to the scene, we can still see that it's still caching. Let me just stop this because it's not quite what I was after. If I play through, we see we've got a nice amount of particles being emitted from the solver, which is kind of cool. We'll fix the look in a minute, but there's a couple of things here. First of all, there's quite a few of them. So what I'd like to do is maybe reduce the number, possibly in a moment. The other thing is we'll notice that we're losing in the thin bit over here. We're losing the thin bit over the edge there. So I'd like to fix that first, actually. That's down to the surface field. If we have a look at the, if we do a volume slice, let's just plug in our cache here, or rather our container. So this container here, this contains all the container information, including the surface field that we need. So let's just display that surface field here. So what we can see is the surface field itself. In fact, let's do that as a primitive properties node instead, because that way we can visualize it as an ISO surface. So let's display its surface field. Let's set the visualization here to an ISO surface. There we go. In fact, let's just split off as well and the voxel boxes. So let's just split off that surface. There we go. So now we just see the surface field. So internally, the Whitewater solver is using this surface field to delete any particles that get too far away from the surface, which is fine on big, thick lumps of liquid like down here and up there. Where it gets really thin, it falls apart. So again, this isn't really designed for thin water. It's more designed for big, oceans and large interactions like that. So I just want to do a little tweak here to adjust this. So what we can do is we can do a VDB reshape SDF. So let's just pop this in here for a minute. And what you'll see, suddenly that expanded a bit because we've set this to dilate. So if I dilate this more, you can see we can make it thicker and thicker. This kind of thing. So I'm going to live with sort of maybe something like 5. Let me just plug this into the into this container bit. So this will allow the Whitewater solver. If we have a look, you'll see we're losing bits over the edge here and sort of running down the thin bits, sort of up here. So now that I've made that thicker, we should be able to see a little bit more detail going on here. Another thing I want to do on the Whitewater solver here is just decrease the voxel size a little bit. Let's put that to 0.01. just because that'll give us a bit of better fidelity in sort of the way we're resolving the noises and stuff. So the voxel size controls the way sort of the other fills and the forces look. And remember, we're quite a small res here, so we want to bring this probably down a little bit. The other thing I want to do actually is to go to the lifespan here. These bubbles, I don't want them lasting for like 5 seconds. I want them to last pretty quickly, to appear and disappear quite fast. I'm going to set the lifespan here to 1. It's more about that bubbliness that sort of bubbles in and then they all disappear. I don't think that the foam is going to last, or the bubbles are going to last that long. The other thing I want to do actually is add some noise to the foam itself. As you run through, you'll see here it's all pretty uniform. So I want to add some noise to create some holes and to break this up a little bit. So what I'm going to do for that is turn on enable erosion. And we've got the repellents turned on. And again, this is a really small scale. So I'm just going to drop this number, add a couple of zeros in, just to make those quite a lot smaller. In fact, let me just revert that to defaults. We've got here 0.5 and 0.9. Let's do 0.005, and we'll do something like 0.02, something like this. So this is the range of scales that we're dealing with. Remember, our resolution of our voxels is 0.002. So this is sort of 10th bigger, so we should get holes around about that size-ish, I'd have thought. Yeah, I think that's all I want to pop in there for now. Yeah, let's create some. Yeah, that'll do. I think we'll see what those settings do. So I've literally just created some noise, some erosion, and the repellents just brought the size down. So the repellents basically are like little dots that apply a repellent force, which create those little holes that you see. And this is sort of the range of scales of the little holes that we'll see. Again, if I don't like this, I'll recache it out just to check. Let's see where we go with that. So on this guy, in fact, this time I don't need to really go into this network here. I could just do save to disk in background directly up here because I've already cached out the source. So let me let that simulate a little bit and let's see how this whitewater might look. So that's going to take a couple of minutes. So I'll just pause the video and then we'll come back when that's done. Now that that simulation has finally cached, let's have a quick look at it. So if I press play, we can instantly see we've got some more stuff happening over the thin areas here, which is good. And we've got quite a bit spreading out as we go, but we're just displaying it as points at the minute. How many do we get? We get about 2 million points, which I think is quite a good amount. So there's another new node we've got with Houdini 20, and that's the whitewater post process. So if I just pop in one of those, so we can run our cache into this first input, our container into the second, and our collisions into the third. Here we've got various options with which we can obviously post-process our particles. And at the moment, you see we're displaying them as particles here. We can, rather we're displaying them as spheres. If I turn that off, we display them as the points. We can also display this as a fog volume. I might need to drop the res here because remember this is quite a low resolution. There we go. So we can also render this as a fog, which I'm not going to do for this example. I'm going to stick with points actually and make that look a bit like bubbly, foamy type stuff. So there's various settings that we can change here to affect the look. So the first thing is we can control the density, which affects the volume density. But in this case, if we set alpha, then we can set the alpha channel of the particles equal to the density, so they kind of fade in and fade off and stop that poppy look. And I think this tends to be quite good. And you can adjust this from the age range. So it's at 0 age, they're transparent, then they fade on over time. They get more dense, which is kind of nice. And if you want, you could even fade them off the end of their life, so they pop up, they disappear at the end there as well. I'm going to leave them fading on like this. Yeah, we could also do it from the normalized age instead of from the actual age range. Remember, I asked them to live for 1 second, so we could set this to 1 here. Or if I did it to 0.5, they're going to fade up a lot faster. So actually, I'm going to leave that at 0.5. We could also use the normalized age range here if we wanted to. And also, it's fading it based on depth. So here is the below the water surface. 0 would be on the surface, and positive numbers would be above the surface. So we're fading in the density towards the surface and then fading it off again as we leave the surface, which is a nice effect as well. So the other thing we can adjust here is the particle scale. So they're going to scale up the bubbles based again on age. So we can adjust that if we want to. So I'm going to set the scale attribute here for the particles. So as soon as I do that, you'll see they go quite large. Because we're using the age range here to set that from. Let me just turn that off actually. I'm going to do this from the normalized age. So 0 to 1. So this is when they're birthed, this is when they die, and you'll see they're scaling up based on their normalized age. Let's put this to 1 so we can see them getting a bit bigger. There we go. So it's a bit of a bigger size there. So in the normalized age here, they're going to reach their full size at the end of their life. If I put 0.5 here, they'll reach their full size halfway through their life. So they just get that bit bigger and quicker. And if I put a little lump here, then you'll see they expand even faster, because I want them to sort of kind of just appear quite quickly, really. So maybe something like this. And at the end of their life, I want them to pop off, actually. So I'm just going to give a very sharp end here on the scale. So as they get really large and towards halfway through their life, suddenly they just drop off in scale. They literally pop small. So this might suggest a popping nature to them and stuff. We've also got from the depth as well, which I'm just going to leave. So maybe let's bring this back a little bit more, something like this. So got those running through like that. So let's just check the density. That looks all very interesting. If we press play, kind of see this noisiness going on with these bubbles as they come through. The other thing I'm not too keen on is all the bubbles end up roughly the same size. I want a bit more variation in the scale of them. So I'm just going to tweak that. This actually uses the p-scale attribute. So what we can do is we can do an attribute randomize. And the reason I'm using a randomize is because here, instead of uniform random, we can use this exponential randomness, which is quite good. This means you get quite a lot of the big ones, a few big ones, even more mid-sized ones, and then a huge number of small ones. So, if you think about bubbles, you do get quite a few, a few big ones, but not that many. And you get a lot more mid-sized and loads of fine bubbles. So exponential is quite a good distribution of that. So let's just rename this to p-scale and make sure it's a dimension of 1, because p-scale's only got 1. And what I'm going to do is put the middle value to 0.002, our particle separation from before. Let's just plug this in and see the effect of that. Oh, there we go. So what we can see is we've got some big bubbles, a few more mid-size, and lots of small ones, which is kind of the distribution I was after. But overall, that's a bit large. So here in the global scale, I can just reduce that down. Let's try 0.5, maybe 0.3, maybe 0.2, something like that. There we go. So now we've got a fine mix of some big ones and some small ones. And it just breaks up, makes that variation look a bit nicer. So let me just flip this up to see how that looks. So we just run through. I'm not too bothered about the bubbles coming down here. It's going to look, by the time I render it, it's going to look a bit more like foam. but I'm more interested in the interaction down here. And remember, a lot of this is below the water surface as well, so it's going to get hidden. But we want that sense of bubbliness and the flow with the water, which is, I think we're getting there, this sort of nice sense of where the bubbles should be. Now, the reason why the foam looks white in water, by the way, is because of the bubbles. You make so many fine little bubbles that it gives it that white overall look, which we sometimes fake with volumes from a distance, but we're this close. I'm going to try and render these to look like that white foamy bubble type thing. So let me just escape that, just to stop that processing. There we go. And yeah, I'm quite interested in that. Let's see how that would look when we render now. So what I'm going to do is just add a null. And I'm going to call this Whitewater Bubbles. So we've got the output here. I'm going to copy this node because I'm going to paste it into another network. So up here, I'm going to make another geometry container. In fact, let's just copy one of these. Let's copy the fountain. Let's call this bubbles. Let's go inside. Where are we? There's the file. Let's repaste in the new path. Ooh, that didn't work. Oh yeah. Let's try that again. Let's select this null, do Control C. Go back here. Let's paste that null in. Oh, that's because that's a file node, isn't it? My mistake. Let's pop an object merge in. That would help, wouldn't it? Paste that in. There we go. Into this object. So now that's bringing in our bubbles. Let's call this bubbles out. There we go. That's all good. Brilliant. So I think I'm quite happy with this bubble sim at the minute. It's a bit tricky to tell until I render it. What I could do, if I just run forwards a few frames, is try and preview it like this. So let me try and run a little flip look at this level, get an idea on how it looks. But remember, we've got the transparency we'll render in a bit later on, so we might see more or less bubbles. But this will give us the idea of the feeling and how it's going to look. And again, I can always come back and run those top networks and resim, resource it, and do whatever. In fact, you could link all your top networks together and have the whole process run through remotely or something. That looks like it might work. Some interesting motion there. These nice splashes pushing the water forwards. Got the little bubbles where it's actually splashing, and then those bubbles pop and disappear. You wouldn't expect to see whitewater foam on, a smallish fountain like this. I wouldn't have thought. Maybe a few bubbles hanging around. We've got a few still extending themselves out there. So overall, that looks very interesting. So what I want to do now is take this over to Solaris and start to texture and render it up. So we'll do that in the next videos.